with a company called Logic Forte that manages information for restaurants. We talked a little bit about that a minute ago. Before we dig into TensorFlow, though, I want to back up a little bit and talk about machine learning and AI and sort of how we ended up getting to TensorFlow. And this quote is especially interesting because this is a quote from Larry Page, from the founder of Google, basically describing what they're working on in terms of artificial intelligence and how they envision the artificial intelligence will ultimately allow Google or a search engine to understand what you're looking for and get that right in front of you. I mean, you fast forward 19 years, what he's basically quoted as working on is the reality. It's pretty crazy to see where we're at now when it comes to AI and machine learning. But in terms of Google's business and search, that wouldn't be possible without these type of technologies. Backing up even further, in terms of artificial intelligence, in 1946, the first digital computer was invented. Fast forward to 1962, Arthur Samuel developed a checkers program that eventually won a match against a checkers champion. Checkers is a pretty simplistic game, so that was the first large accomplishment. Chess is a bit more complicated, but in 1997, IBM developed software that defeated reigning world champion. So there was quite a gap between 1962 and 1997. It took a while to get to a point where you could have the computer learn or a strategy required for chess. Fast forward a little bit more, another 10 years, Netflix launched a prize competition that was intended to develop software that could beat Netflix's own recommendation in predicting a user's rating for a film. I don't recall exactly when that competition was launched. I want to say it was before '09, but they recognized a winner in 2009. So at that point, technology was to a point where AI could beat out Netflix's own algorithm at predicting a user's rating for a film. A couple years later, you probably remember when it came to Jeopardy. IBM's Watson beat two human champions in a Jeopardy competition. So now think about with checkers and chess, machine learning is having to think about very specific information. It has a fixed set of points and only so many possible moves. When you move forward to looking at movie user ratings and Jeopardy competitions, you're having to deal with a much larger set of data. Even more so with Jeopardy than with Netflix project, because I mean, for those of you who've seen Jeopardy, almost any question is fair game, and so the amount of data that has to be accessed and understood is just amazing. And the fact that a computer gets to a point where it can understand the question and it can make sense of information to answer the question is pretty impressive. Though that was 8 years ago. So just a couple of years ago, AlphaGo beat the #1 ranked Go player. How many of you have played Go? All right, so you're probably familiar with this, but for those of you who haven't played Go, there are many more possibilities in that game than there'd ever be in checkers or chess by a long shot. And it was believed that it would take many more years to get to this point that AlphaGo accomplished in 2017. So another pretty amazing feat in terms of computer strategy and AI. Now, last year, 2018, a couple big milestones worth pointing out. Alibaba, a lot of you might have recognized that name from sort of the Asian or Chinese version of Amazon, a large online marketplace in the East. They developed language processing AI that could outscore top humans at Stanford reading and comprehension tests. So they got to a point where their AI could score 82.44 against basically 82.304. Barely better, but the crazy part is AI has gotten to a point where it can read and comprehend better than the best humans, which leads to even more exciting things like Google Duplex. Assuming most of you are familiar with Android and Google Assistant and things like that, Google announced something that I'm gonna share in just a second. We're gonna play a short video, but this video demonstrates their version of Assistant 2.0 and how it can be used to book appointments over the phone. So you're basically telling Google's Assistant, book a haircut with Sue at on Tuesday at 2, and then Google's Assistant in the cloud will call a phone number and have a conversation with somebody, which means that they have to understand not only textbook material and formal reading and writing, but the oddities that you'll run across in either different dialects or different types of speech. Like I said, I'll demo that here in just a second. And then finally, future-wise, they're expecting that AI will outperform humans by a long shot, starting with exceeding human capacity in translating languages in 2024, doing a better job of writing high school essays than, I'm assuming, high schoolers in 2026. So maybe not saying a lot, but driving a truck in 2027, starting to think that that time frame is going to be shorter and shorter than they're anticipating with the advent of things like Tesla's semi-trucks. Working in retail in 2031, so imagine a retail store that only has customers. Why would you need people staffing the store if you've got AI? And then writing a best-selling book by 2049. This is where it gets interesting. Have any of you seen the demonstrations where they talk about AI making songs or making stories or anything like that? It's impressive, but still traumatic. It's not something that you want to listen to or read, but the fact that it can sort of put together ideas, whether composing sounds or composing stories and trains of thoughts, are pretty amazing. So to say that in 30 years AI will be able to write books that entertain us is pretty crazy to even think, just knowing where the technology is today. And then finally, in just over 40 years, if you're needing brain surgery, you're not going to call a brain surgeon. You're probably going to rely on an AI, which hopefully they get that right. But I'm going to show a quick video, a couple-minute video that talks about Google Duplex, and then we'll switch back to the slides. And we're going to get an ad, I'm sure. Oh, man. I'll send them a bill. So while we're waiting for this to get to the piece, this is from last year from a Google conference. And he's talking about the upcoming Google Assistant that's still in the works but about to launch.
client. I'm looking for something on May 3rd. Sure, give me 1 second.
The crazy part about this is that
Sure, what time are you
the
looking
pauses
for around?
and understanding some of the weird
12 p.m.
speech.
We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like, what service is she looking for? Just a woman's haircut for now. Okay, we have it 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks, great. Have a great day. Bye.
And they have another demo where they call a restaurant and make a reservation with the restaurant. Definitely worth a watch. So if you pull up the slides later and click on that link, it'll take you directly to that video and you can skip ahead. But the crazy thing about the restaurant piece is it's even harder to understand the person at the restaurant. I can't remember if it was their accent or background noise, but it was truly impressive that it was able to have that conversation with the person, even when the person would ask strange questions or not or maybe be distracted or whatever it was that led them down a strange conversation path. Google Assistant was still able to pick up the cues of what that person was asking or how things went awry and get the conversation back on track and make a successful reservation, which is pretty crazy. And they're talking about those type of features allowing Google to bulk call businesses, which is happening now, and ask if the business is going to be open on Veterans Day, which just happened last week, or Christmas Day, or Christmas Eve, or things like that, so that they can automatically update their Google Maps to say, this business is closed on these days, without waiting for the business to submit the information. I don't know how many of you have met Daniel with Google that's been to a lot of different tech events here locally, but he's talked a little bit about this and mentioned that it's still in the works and that they're pushing forward with it. It's given them some issues to where they didn't launch it last year, but he said it's just a matter of time before that's a reality. And right now, if your business is getting those calls and you don't like those calls, you can go out and you can shut them off. Talk to me afterwards and I'll show you how, because I just ran across that setting the other day. I didn't shut it off, but I found it. But with all that being said, the reason that I cover this background is because as these technologies progress, they rely less on smaller code bases that have to understand, for example, with checkers or chess, the types of moves that need to be, the types of moves that are allowed, the types of strategies that might, that the opponent might try to pull on you, things like that can be sort of encapsulated in a smaller standalone program that a person could write line by line. Whereas when you get into some of these more advanced technologies, the only real way to cover all of the different edge cases and learn the difference between different types of speech or different words or what we're going to talk about today, different images, is to feed the computer system tons of data and allow the computer system to hear or see or read whatever information it is that you have, so that it can start to understand patterns and find patterns, whether it be that all of these photos are birds or hot dogs or shirts or shoes or whatever it might be. And that's what we're gonna dig into tonight. We're gonna talk more about how those models work and what they look like, and if you have some sort of use case where there's not already a model that can help you, like let's say you have a ton of photos and you just want to know if the photos have one person, two people, three people, no people, You can upload those photos to an existing service, or you can download a model and run that model locally, and that model will tell you those answers. You don't have to do everything we're doing tonight to teach the computer that there are people in a photo. That's pretty basic stuff. But you'll get a better understanding of how that happens as we walk through this TensorFlow demo, because TensorFlow is one of the machine learning frameworks that you use to build these models. And then if you have a unique need within your business or a project you're working on or a hobby where there just isn't a model that can maybe find photos of whatever widget it is that's coming across an assembly line, or analyze maybe certain types of brain scans in a medical usage, you'll understand how you can prepare the data that would be fed through the system to help it try to better understand what those cases look like. Like, this person has brain cancer, this person does not. Now, I'm jumping a little bit ahead. When you're building those models, you'll typically use a machine learning framework. In the early days, those frameworks were, Theano was one of the earlier frameworks. We're talking about TensorFlow tonight. That is a framework that was open sourced by Google in 2015. That's the red line on here, and if you see the spike early on, that's when it was released. But PyTorch is another very common framework, and you'll notice that Keras is tends to trend alongside TensorFlow. And we'll talk a little bit more about this in a moment, but as Keras was designed to make TensorFlow easier to use. The gist of the workflow, well, we're going to cover that in just a second. I'm not going to jump ahead. But with these machine learning frameworks, down at the bottom, I also list a bunch of other frameworks. I mean, you've got frameworks that Microsoft and Amazon have developed, a number of independent frameworks. You can go into Google Trends and try to see which ones are more or less active. Some of these are dying off, while others are just getting started. When you're if you're in a situation where you're wanting to build out a machine learning model, the framework you use will depend partially on the software language you're used to. TensorFlow and PyTorch and Keras are all using Python, but some of these other frameworks use other languages. So if you're in the Microsoft camp, you might be looking toward CNTK, or if you are all in on AWS services, you might be looking at their MXNet product or their SageMaker services. So it really just depends, but the process is about the same for each of these. Now, when it comes to a machine learning framework like TensorFlow, there are a variety of uses for these frameworks. TensorFlow in particular, here are 6 of the more common uses. Mozilla uses TensorFlow to drive their open source speech to text engine called DeepSpeech. Google uses TensorFlow to develop their RankBrain algorithm that is one of the components in PageRank or their search engine rankings. Google also used TensorFlow to develop the Inception image classification model. That was one of the first image classification models that was an outcome from the ImageNet recognition challenge back 5 years ago. Smart Reply, for those of you who use Google Apps or Google Mail, or even Google Mail on your mobile device, and you start to type a message, in the early days, it would try to complete your words. Now it tries to complete your sentence. That completing your sentence is based on Google's Smart Reply. And the beauty of these models is that a model like Smart Reply can live on your device. when you're typing, it's not necessarily sending everything that you're typing back to the cloud. They've gotten to a point where these models can be trained and small enough that they can live on your computer or in your browser or in your mobile device, and it'll just feed the text as you're typing into the model, and the model continuously provide feedback. Google's also working on networks for drug discovery with TensorFlow and on-device vision for OCR. Those are just a couple of the use cases. We're going to be talking about the image classification. Now, as far as image classification use cases, you could have a model that recognizes handwritten digits. I mean, think about, for those of you who still remember checks, filling out a check, and in the last decade or so, the banks have relied heavily on handwritten digit classification, where they'll basically do handwritten OCR on a check, and they'll say, okay, this check was handwritten for $52.52, and that's an example of a machine learning model at work. There isn't a banker sitting there typing every single amount on every single check anymore. That's how you're allowed to deposit checks at an ATM, or take a picture of a check and have it automatically recognize the dollar amount. They'll still verify them on the bank side, so you don't get any crazy ideas, but it saves them a ton of work, if you can imagine. Image recognition is another big use case. I mean, all of these are very related, but the difference between handwritten digits literally being hundreds of thousands of ones and twos and threes and fours written by hand in different ways versus image recognition is that with handwritten digits, you have a pretty small set of numbers. I mean, it's a lot easier to train to know, is this a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, versus when you get into image recognition, those models can become a lot more complicated and a lot more impressive. Rather than spitting out a number, they're able to, like I said earlier, tell you there's one person, or there are two people, or three people in the room. They've gotten so far as to be able to say person 1 is smiling, person 2 is frowning, person 3 is speaking. They can give you some idea of what's happening in that scene without physically looking at the image yourself. They can also recognize what is in the image above and beyond people. I mean, that's a simplistic use case. If you upload an image to most of these image recognition services and it's a scene of a living room, it'll say that you've got a couch and you've got maybe a love seat or recliner and a painting, a lamp or two. It's pretty amazing. I mean, if there's something that can be classified and put into an image, these image recognition services can identify it. They've just basically trained on so much data that they can recognize quite a bit of stuff in these. I'm going to breeze through some of these others just for sake of time. Word embeddings, recurrent neural networks, natural language processing. That's what drives things like the Google Assistant. Let's see. We're going to focus on image recognition. Here's basically what the flow looks like. I'm going to go through a demo and show you, but it's pretty simple, so I want you to understand sort of what's happening behind the scenes, and if you ever need to develop your own machine learning model, you'll have an idea of what to expect. I mean, first off, you need a concept. You need to know what it is that you're going to train, and then absolutely the most important piece of developing a model is preparing your data. If it's sort of garbage in, garbage out mentality. If you don't have good data to train a model like this, it's just not going to work. I mean, imagine with the handwritten digits, if you have a whole bunch of digits 0 through 9, but you told it that a 1 was a 2 and a 2 was a 4. I mean, it'll never figure out what is what. Or if it's not a number and you tell it it's a number, it's just the same. It's gonna see these anomalies and get confused easily. So it's super important that you prepare your data, and basically what you'll end up with, especially with images, is you'll end up with a label of some sort with every single image. So if in the case of the handwritten numbers, or in the case tonight where we're going to identify clothing, the numbers, every single image will either have a 0 or a 1 or a 2, and you could probably even name the files with those digits, or you could embed the data, or you could have, there are a number of different ways you can feed the data. You could have an image file and then a text file that has the actual data inside the text file. One way or another, you have to be able to tell the computer what's in the known images so that it can train on those, and then it can start to guess what's in unknown images. But once you've got good data, when it comes to more complicated models, you'll plan your model. I mean, you'll find that what we're doing tonight is hopefully straightforward. Develop the model. I mean, this is going to be a lot like software. Coming up with a software concept, planning, developing the software, and then in our case, training and evaluating is feeding it that data with those images and the labels, and then looking to see how well it's doing. Typically, let's say you feed it 50,000 photos. You might hold back 10,000 of those photos and use them as training. So you'd feed 40,000 photos, let it learn from those, and then take these other 10,000 photos it's never seen and evaluate the performance of the model based on how often it got those right. But basically, when you're training and evaluating, you might bump back to developing your model some more. You might have to bump all the way back to preparing data. If you're just not getting the results you want, there might be an issue with your data. But then finally, you can deploy your model, and that could be just on your computer, that could be out to the cloud, that could be out to mobile devices like I was talking about. These models are literally just a data file, and the data inside them ultimately is a set of vectors. It's not storing images in the file. It's basically boiled down whatever it is that you're feeding it to something where it can use it can say a bird is this vector, a shoe is that vector, and so you have a set of these vectors in that data file that then when it starts to analyze future images, it can use the same model to boil that down to some sort of vector and say it's close to whatever this is. So the files are surprisingly small considering what's in them. And then if you have, let's say you're teaching a system to identify fraud, very common use case that's not necessarily easy to come by because that can mean so much to so many different people or companies. You will just keep feeding data into the system on an ongoing basis because people find new ways to cheat the system. Maybe you've been accepting credit cards and debit cards and Venmo, and now you're accepting Grubhub or whatever at a restaurant. There are going to be different fraud patterns with those, so you need to be able to continuously feed data in and train your model. We're going to focus on training and evaluating tonight. I know we're running a little short on time, so I'm not going to dig real deep into the changes in TensorFlow 2. If you brought your lab coat and want to talk data modeling and building models afterwards, I'm glad to stick around and talk shop about this stuff as far as deep dives. But the gist of the changes in TensorFlow 2 is that they're really focusing on ease of use. It's a lot easier to build models in TensorFlow 2 than it was in TensorFlow 1. Part of that is just the tighter integration with Keras, which ultimately was meant to make TensorFlow easier to use. But it also makes the models more portable, so you can have larger data sets accessible to mobile devices and tablets and things like that. But with that, we're going to dig into our demo. I've got a link in the slides if you happen to pull them up in case you want to follow along. The gist of it is their demo for TensorFlow 1 was showing you how to classify handwritten digits. Their demo for TensorFlow 1 later evolved to identifying and classifying different types of clothes. I guess they just figured people would find that a lot easier. And it is interesting to understand sort of how it works and see a more practical use case that's above and beyond. You've got a 10% chance of getting it right, you know. With that, we're going to jump over to this this link on the bottom of this slide if you're following along and want to know where I'm going. And so my demo queue slide. All right. So before I start the demo, for those of you who haven't been to the TensorFlow website before, I'll just a quick navigation. The very front page has it getting started with TensorFlow. They talk a little bit about what the possibilities look like, and then they have building out your first neural network, which is what we're going to talk about today. But they also have a few other demos. And then they have a whole gallery of things that you can walk through. So if this is something you're super interested in using at work or on a project, tons of resources out here. In a few months, I'll be revisiting models and talking about why it's so important to protect your models, and I'm going to demonstrate how you can basically trick a model into thinking that maybe a dog is a cat or something along those lines, so that you understand what that looks like and how to protect models if you are using machine learning and you've built your own models. But we're going to go to this tutorial. I just clicked on your first neural network. It brought up this demo where we're going to classify images of clothing, and I'm trying to make sure I don't glaze over anything that and take anything for granted here. When you're in this demo, it's gonna show code, and it's gonna talk about the process that we're gonna go through, but it also has a couple different ways to run this. We're gonna run this in Google Colab, which is basically an online website that allows you to run Python code. So how many of you here have written in Python? Okay, quite a few of you. How many here have ever used Jupyter Notebooks or anything along those lines? Not as many. So Google Colab is pretty much Google's version of a Jupyter Notebook. And for those of you who have never used that, picture a website that instead of just being powered by Python, where you've written code to display pages, you can interact with the page. It's a cross between like a Python developer tool and WordPress. It's like WordPress for writing Python. It's pretty amazing. And so you can have text alongside it. We're going to see that here in a second. But we're going to go into Google Colab. You could also download all of this from GitHub. And so I've sort of navigated to the area in the repo where you could download this. We've got an image classification model here. It's a single file that you would open up in Jupyter Notebooks locally. And then you have the option to download that notebook file directly if you don't want to browse to it. So this is what it looks like. IPYNB. That's the extension for Jupyter Notebook. All right, we're going to reconnect. I clicked on the Colab link. I'm going to reload it completely just to make sure that I have a new runtime. So when you fire this up, let me make sure that we can see this okay. Can you see this all right in the back? Awesome. So we're in a Jupyter Notebook. You have some stats related to RAM and disk because you're browsing a web page, but behind the scenes, it's running Python on a private server that has a fixed amount of RAM and disk space. So you can't go crazy. You can't run something in a loop or process tens of gigs of data because you'll run out of memory or disk space. But you can certainly run through models like this that don't take a lot of overhead. And so as we go through this, we're going to download a bunch of images into this virtual server, but we're interacting with it the whole time through a website. And let's see. So for those of you who haven't seen Jupyter Notebooks or anything similar to that, you have the ability to put text in here, links in here. Whenever you see one of these arrows, this is a code section. And if I click on the code section and click play, it actually runs that code on the server, and it should return information right below the block. So we're waiting for it to run and return. Usually it's a lot faster than that. That's the downside to the live demo life. Let me see. Okay, so it is working. This is supposed to say TensorFlow version 2 below, but it didn't. But it's working fine because when I click on this, you can see some output at the bottom telling you that it's running this code. It's basically importing the TensorFlow library, importing the Keras code, importing NumPy, Matplotlib, and then it's printing the TensorFlow version, which we're running on 2.0.0. And now, this literally, because of the format here where you can run code and you can have documentation in a notebook, it's going to tell us exactly what's going on here. I'm going to glaze through a little bit of this and give you the gist of it. But we're basically importing 70,000 grayscale images from 10 categories. And you can see here that there are shirts, and there are shoes, and there are pants, and sandals, and bags, and different things like that that we're going to train on tonight. It's they basically consider this the hello world of machine learning. And when we do that, we're going to use 60,000 images for training and then 10,000 images for testing. A lot like I talked about earlier, where we're going to hold some of them to the side. Because the problem is, if we used all 70,000 images for training, it's going to know all 70,000 images. So if we feed it an image and we're all proud of our model for getting it right, that's a false sense of security. Of course it got it right. It's seen the image before. We told it what it was. But we're going to go ahead and click on this code that's going to download this Keras data set called Fashion MNIST. And you can see in real time that it's downloading these files from Google Storage. And I believe it's done. So we're going to keep moving. It talks a little bit more about the data set returns. Now, when we're building these machine learning models, we're not building them on some 20 megapixel picture of a shirt or of shoes or anything crazy. We're not analyzing a huge image file. Scrolling back up here to these pictures, you'll notice that they're pretty small, and if I zoom in even more, you'll notice that they're not super detailed. They're not even in color. The fact of the matter is, for this type of training, you don't need a lot of detail for it to recognize the difference between these. Now, when you get into your more complicated image models where it can recognize a variety of things, like pretty much anything in the scene or the picture, it's going to use more or higher res and color images. But for this, because if you ran something through and you wanted to know what color of chair was in the picture, you'd have to you'd have to teach it what colors are. But for this, we're purely wanting to know what type of article of clothing is in an image, so we aren't concerned about color or high resolution. So we've downloaded this. The images are basically 28 by 28 pixel images. Those and because they're grayscale, the grayscale colors range from 0 to 255. And so you can picture you have an array of 28 by 28 numbers, and each number is going to be 0 to 255. That's what we're feeding in. And then each image has a label that's either a 0, or it ranges 0 to 9, and then we have a key that shows us that a 0 is a t-shirt, or a 3 is a dress, or an 8 is a bag, and so on and so forth. So when it has learned this, it learns that it's an 8. It doesn't learn that it's a bag. But then when it tells us, I think this is an 8, we can do the translation on our end. So we're going to feed it that list, that map, so that then when it does show us something, it can show the labels. And now we're looking at the shape of the images, and you can see there are 60,000 28 by 28 images in here. And then when you check to see how many labels there are, you can see there are 60,000 labels, which is good because this is an easy way to make sure that all of your numbers are driving. You don't want to find out you're pulling in the wrong file or something. And so we're going to train the labels. We're going to look at the shape of the test images. And you have 10,000 28 by 28 images. We're going to check the length of our test labels. There are 10,000 labels. All of that makes sense. Now we're going to pre-process the data before we train the network. And you can see that this is sort of a representation of, I'm making sure you can see what I'm seeing here. This is a closer representation of what it's seeing. That makes it easier for us, but ultimately at the end of the day, instead of being a 28 by 28 array, it's probably being fed just a long list of numbers. So let's see, we're going to scale this so it's dividing by 255. Let's see, we're verifying that the data is in the correct format, and so now by doing this, this is basically showing us the first 25 images and their labels, because we want to make sure that we didn't mess up along the way. Like garbage in, garbage out. So if this doesn't make sense or look right, you know you're in trouble. But the data we're getting ready to feed it does show that this is a sneaker and that this is a t-shirt and these are trousers. So all of that looks fine. And now we're going to build the model. You have to set up layers for a model, and this goes into a lot of detail here, but basically you're taking your image and flattening it into a series of numbers, and then you're running those through multiple densely connected layers, and this could be a whole nother talk, but basically when they're talking about designing your model or coming up with a plan, this right here is where you would spend the most time. You'd try to figure out what am I going to do in terms of converting my image or my audio or whatever it is that I'm analyzing to something that the computer can use, and then what kind of layers are most likely to be successful in analyzing the data and learning from the data. And you might end up trying tons of different combinations before you finally get something that you're happy with. But they've already selected layers for us. We're going to compile the model. Basically, we're compiling those layers, and then we're going to train the model. And now when we're training the model, at this point, it's literally reading those 60,000 images and running them through those layers that we just described. And it takes a little bit, so I'm backtracking while it's training, and then it's optimizing them and dealing with loss based on these settings here, and then these metrics are what determine what we're seeing during the training. And so if we scroll over just a little bit, we can see in real time that the accuracy starts out at 68% and then bumps up to 75 and 79 and 81 and 82, and that's based on I believe that's based on the training data and the test data that we held aside. I'm pretty sure that it's looking at that test data in real time, but it could just be a feedback loop where it's estimating that. No, I take that back. It's not looking at the test data at all at this point. Is it?
It is looking at the actual data.
It's just looking at the actual data. The next step, we're going to compare this 83% accuracy that it thinks that it achieved to the real accuracy. So this step, where we're evaluating the model, is where we're feeding, our model understands how to read these images and score them, and we're going to feed it the test images at this point. So this is where it's going to tell us how accurate it really is. So it thought that it might be 84% accurate, but based on the images that we set aside, the 10,000 it had never seen, we're at 82% accurate, which is close, but you just have to be aware that it can sometimes be fooled into thinking it's more accurate than it is. But this gives you a really good idea. 82% of the time it's going to get it right. And going back to this where it was training and it went through here 10 times and looked at it over and over, and you can see that it thought the accuracy got better as it kept going over those images. Every time it goes over those 60,000 images, it might pick out something that it didn't notice before, or it makes some connection as it develops its model to where by the time you get to that 10th iteration, it's becoming more and more accurate. It's not uncommon with models in production to iterate dozens of times or hundreds of times to get to the point that of accuracy that you're wanting. But you will hit diminishing returns at some point. If you run it 100 times, it doesn't mean that it's 10 times more accurate. If you run it 1,000 times, it doesn't mean it's 100 times more accurate. At some point, it'll plateau or even start. If you can generate graphs that show this accuracy trend, and you can see where it'll start to drop off, and it doesn't make sense to train after a certain point. But that's the part that takes tons of CPU or tons of GPU or tons of tensors if you're using specialized hardware to train models. And so if you are training a big data set, you can pay by the minute or by the hour to use cloud resources to train something in minutes or seconds that might take a month on your laptop. And so ultimately you end up paying the same amount of time whether you tell it, I want to train in 5 minutes or 1 minute. So the beauty of the cloud is it can just scale up and do all of the training that it needs to do without you waiting around at a fixed price. So we evaluated the accuracy. Now we can make some predictions. We're about done here. We're loading the prediction side of things. And now it's showing for the first, the zero, it's at a zero index, but for the first image, you can see behind the scenes what it's seeing. It's predicting what that image is, and you'll see the image in a moment, but you basically have an array showing that it's this amount of accuracy for image 0, it's this amount of accuracy for image 1, and for those of you who maybe recognize scientific notation, those might as well be 0. It's a 0% chance of those. It definitely knows it's not 2. It's like zeros across the board. So I'm looking through here, and you can see that it's most likely this one, image 9. And so it's describing that basically that's the model's confidence. And normally when we read that, it's going to show 0% chance or 20% chance or 80% chance or 90% chance. But all of those different things, if you're in a situation like this, if it has a choice and you're saying it's one of these 10 things, it's going to rank all 10 possibilities. Most of them are going to be close to 0, but if you add up all of the percentages, they add up to 100. So it might say one of them is a 90% chance and one of them is a 10% chance and the rest are 0. But ultimately, all of these numbers add up to 100%. And then it's telling you when you run this code, all of these little segments I'm playing, these are just Python code. It's using NumPy to find which number in this array is the largest number, which argument is the maximum one of these predictions, and it's saying 9, which is what we figured out just by eyeing it. And then we can the model is most confident the image is an ankle boot or class 9. So the label 9, let's graph this and look at the 0th image. And so this is basically, this code is plotting the image. Oh, don't go backwards on me, please. I almost swiped back. This code is plotting the image, and this code is plotting the value array. And when you look down here when we run this, you're basically running those two functions. So we're basically telling it, we're asking it to show us the image for the prediction and the percentage and such. And so the human version of the outcome shows a boot, and it shows that it was 94% likely. So if we look at our data up here, you can see 9.39 to the net minus 1, which would basically be 0.939 or 93.9%. And the ankle boot is the 9th one. And so you can sort of see a visual representation of what else it thought it could be. Now, these are very light. I mean, these two combined only add up to 6%. So this is helpful for troubleshooting. The area that you get into trouble with is if you always assume that the top answer is the correct answer, you can get into a bind, because you might have something where it's 50-50. It might say this one's 49% likely and that one's 49.5% likely, and then this one is 0.5% likely. It really doesn't know at that point. You'll have to set a threshold and say, if it doesn't know to at least the 80 or 90%, we're not gonna show an outcome. Question?
What were 5 and 7?
Well, that's a good question. Let's go and see. I'm pretty sure we have a list here. Yep, 5 and 7 were sandal and sneaker. So that makes sense. Yeah. So they had characteristics of a shoe, but they weren't a boot. Good question.
So that would be like with Google.
Mm-hmm.
It automatically assumes the person based on facial recognition.
Yes.
However, you do get questions every once in a while. Is this the same person?
Correct. And
Because
it'll
they
suggest.
have a threshold, but a lower threshold to say if we have something in this gray area.
Absolutely. And so yeah, if Google or Facebook or iPhoto or any of those tools are analyzing faces, and they come back and you'll notice that sometimes they just know who someone is, that's coming back to this, what's happening behind the scenes with the model. It's basically saying, I'm 99 or 100% sure, just because it's probably seen an image so similar that it says there's no way it's not that person. From the machine perspective, it's high confidence. It could still get it wrong because it could be a twin or something, but but then if it is asking you, is this Bob or is this Sue or is this Sam, that's exactly right. It's basically high enough confidence that it is willing to ask you, but not high enough confidence to just say, this is Sam. So yeah, that's exactly how that's working behind the scenes. And then this is just showing another one where it analyzed the next one, and the next one it thought was a sandal with 66% confidence, but it was a sneaker. So going back to where you set that threshold, in this case it was 66% sure it was a sneaker, and then most likely 34% sure that it was a sandal, and it just got them wrong. But that's an example of where it didn't have good enough data to get it right. And that's the gist of it. This goes on to plot a few different photos and their predictions, so you can sort of see how that works. I mean, like in the case of the trouser, it was 100% sure. But in the case of some of these others, like this pullover, it thought it was a pullover, but it was really a shirt. And I mean, that's sort of your 50-50 split. It got 43 here and maybe 38 there, and then it was just sort of all over the board. And those were probably other variations of shirts and coats.
How does it know when to backtrack? Like, if I'm on Facebook
Mm-hmm.
and it's like, is this Sam? Like, hell no, it was a picture of Bill.
Right. And it learns from that. The continuous learning, if you tell it, no, this is Bill, it's going to take note of that, and it's going to probably go back and retrain and go.
But I mean, what if it's really Sam?
Yes, that's where you get the weirdness. That's the garbage in, garbage out. So if you're telling it at somebody else, that's just as good as telling the number recognition that a 1 is a 0 or a 5. At that point, you do a good job of confusing it. A lot like when if we have family images in something and I tag our daughter as my wife so that she sees that picture. It doesn't know which one's my daughter or my wife, but it tends to always pick those two out and think that they might be my wife. So that's a great example. At that point, it's confused enough because it's seeing two different things, and you're telling them that they're both the same thing, and so it's like, oh, is this her? But yeah, Beth.
Did you see the article or the write-up of it was the self-driving car accident that was in Arizona?
Yeah.
The confusion was caused by the algorithm trying to identify. It's like, well, this is a person, and then that person moved and had a bag on their shoulder or something. It's like, no, it's a bicycle, which caused it to reprocess. And it's like, no, this might be a parked or stationary object, which caused it to reclassify.
Yeah.
And it got in that reclassification loop, it could never pick out that it was a person.
Yeah, bad
And
deal.
that's what they eventually said caused that accident.
Yeah.
Another example of confusing it.
Mm-hmm.
Self-driving cars.
Yes.
You put in the taking and drawing the road dividing line and taking it to the ditch.
Mm.
Goes and drives in the ditch.
Oh, yeah, I believe it. No, they've made great strides with the self-driving cars and being able to figure out what's happening in the roadway, but it's not perfect by any means. And you'll see where companies like Tesla are taking a pretty aggressive autonomous approach to this, where all of the cars are fleet learning. And the interesting thing is, when Tesla came out here for their first test ride event, where you could hop in and they're not willing to do a test drives unless you're serious, but they will do test rides where they'll take 3 or 4 people at a time. They specifically said that it was their first time coming down to Springfield, and they wanted to make sure the event was successful. So they come down here hours ahead of time, and they will drive the different routes that they plan to take people on, so that the car can learn from the route, and then that learning is fed back to Tesla so that the other cars that come to Springfield also learn from that. And so it's still not perfect, and you can get into situations where if that's your first time in Springfield, that your story reminded me of this, and you drive your Tesla in the ditches, guess where the rest of the Teslas might drive? People aren't doing that, but that's certainly a risk of the fleet learning and sharing these models. So you have to be, I imagine they've got some way to deal with this noise, or maybe cars that go off the GPS track or whatever is happening, but then you've got other vendors that are taking a more conservative approach, and rather than trying to learn just how to drive in general and then picking up on cues from making that first track, they are only doing autonomous driving on known tracks. I mean, Tesla is claiming that they can drive anywhere even if the car hasn't been there. They just do a better job once it's been there. Whereas some of the other cars, if that brand hasn't been there until now,
Like GM.
yes, GM's the example I was thinking of with their newer models. They won't auto drive through those areas, and the same holds true if they notice any discrepancies. And I think this applies to any of the platforms, such as cone areas, so road construction. They'll refuse to drive. They'll disable the features. Yeah, question?
You develop AI for your company?
I'm an aspiring AI developer.
Okay.
I wouldn't say I'm an expert. We've done some work in the field, but nothing lab coat worthy.
Nothing what?
Lab coat worthy.
Okay, but what kind of problems have you tried to tackle?
So the issue is, for us, our problems are more time series related. So
Okay.
let's say you have sales over the last decade, and this could be transactional information where you can see every single time somebody orders food, or it could be summary data showing every hour of data or every day of data, and you're trying to pull out trends from that. It's a little bit more of a custom use case because you have to train on the data that you have. There isn't really a model out there that knows what your data is going to do.
What is it you're trying to predict, though?
Usually we're trying to predict sales volume, and more importantly, not dollar amounts, but how many visitors are coming through, and how many pieces of burger patty need to be prepared ahead of time and things like that. We're trying to estimate what does the team need to have ready to go when the lunch rush hits, what needs to be ordered the days or week ahead of time so that the food truck has the right amount of food, how many people need to be on staff so that you're not waiting 5 minutes for a 1 minute order, stuff like that. So the problem with time series data is that you have to be able to pick out information that will sway your trends. So special events, whether that be self events like we ran a promo on Tuesday, or external events like homecoming, or school is closed or school is open, or whatever that might be, and find a way to track those and feed that information in so that your model understands that traffic isn't going to spike on the whatever day of August when school starts. It's not going to spike on that Thursday. It's going to spike on whatever that day is. So then you can tell it, here's the school schedule for this restaurant that's near a university, and that helps the model understand what could happen.
So do you treat that like seasonality?
Yes.
Do you define what your seasonality is? It doesn't have to be like Christmas and Thanksgiving.
Yeah, sort of. It's unfortunately we don't have it quite nailed down. We get better results than the old way of doing it, but we're striving for something above and beyond where we're at now. That it used to be that people would estimate this information by just literally averaging the last 4 or 5 weeks of sales, and they're like, well, this is what the last 4 or 5 weeks looked like, so this is obviously what Friday is going to be, and it gives you some idea, but it's not the right number amount. And so what we're doing gets you closer to the right amount. I mean, it's better than just that average because it's accounting for trends. Even if it's an upward trend or a downward trend or some of these special events, but we're far from having a perfect model where we're 99% accurate. But we're definitely not 60% accurate like the old way.
I mean, I think that problem exists for many fields.
Absolutely.
Not all in that it's not the problem itself isn't in the computational component. It's in do you have the information that's relevant to make the prediction?
Absolutely.
So the more you brought into that data set based on what might matter, then the better job it could do.
Yeah.
If it's not in the data set.
Right, you nailed it. And it's not going to be able to pick out, it certainly can. There are tools that can pick out a lot of pretty amazing patterns and help us identify anomalies that you might have never noticed otherwise. But in terms of time series forecasting, you're seeing some activity with some of the big players, like Amazon just announced Amazon forecast maybe Q2, Q3 that has some potential, but the problem is it doesn't have access to that data. I mean, it can certainly look at your data and try to pull some things out, but if you have external events that don't have a pattern, it's not going to be able to pull out the pattern. You have to have some way of feeding that data into your model. And so those are the issues we're trying to tackle now. Yeah.
I was just curious, do you have weather in your model?
We do. Mm-hmm. Because absolutely, depending on the brand, a rainy day could be really good or really bad. And then you want to look at a lot of other conditions. I mean, it could be temperature, it could be wind, it could be how long it rained or sort of time of day. I mean, it can rain mid-morning and not hurt your sales because you might have a slow mid-mornings. But
I don't know if you deal with third-party deliveries. I don't know.
Yeah,
if it's Sonic, but
Grubhub
other
and things like
brands,
that.
yeah, so
Mm-hmm.
that brings in a whole new complexity
Yes,
in this
yes,
predictive
you're
model.
absolutely right, and we're able to see what that volume looks like by order type, so that helps us a lot because we can know that these orders paid by cash, these orders paid by credit card, these orders paid by Grubhub, these paid by Uber Eats, whatever that might be, and so we're able to look at that.
I mean, at this point,
they're it's premature.
It's still, yeah, that's what I'm saying.
But it's gonna
just
become-
starting. I
yes.
mean, you won't have as much data to run the.
You don't, but what we anticipate is that as they run promos and different things in different areas, or they come into an area, once we have a handle on what that data looks like, if we know that Grubhub or Uber Eats are coming into an area, we can account for that and pad their sales, because you might see a little bit of a bump depending on the brand. So that's a perfect example of something that needs to be accounted for. And there are just so many variables, it's almost overwhelming, but we're super excited about the possibilities. So yes, as far as developing AI for the company, I mean, we're doing a lot of work, but not to the point where it's Sandia Research Laboratory or anything like the.
Are you selling it to customers yet?
Some of it is incorporated into our reports, but it's but we're light on the integration, because our opinion of machine learning and AI is that we need to be able to explain exactly what's happening and be able to tell you this is why you're seeing this trend. And up until now, most of the machine learning has been more of a black box. Think about a lot of these things that we talked about tonight. It works, but not just everyone can tell you what's happening. And I find that pretty alarming for a couple of reasons. Number one, if you don't know how it works and all of a sudden it stops working, you're in trouble. But number two, there's an ethics side to it. With what we're doing, I mean, if you're able to prove accuracy and have good trends, so be it. But if you start using things like machine learning in the justice system, and it's the difference between somebody going home versus getting a fancy hotel for 5 years, you want to be able to tell them why it went one way or another. And oh yeah, absolutely. And the problem is the models aren't, with it being a black box approach, it's hard to prove that. You just know that until it's too late, when you see the trends and go, oh shoot, we just sent like so many people to jail or whatever it was, and this many of the cases have been reversed, and we realize there was a bug, our bad. I mean, that's just not acceptable. So yeah, that's partially why we're going light on this. We want to be up to speed on it, and we will let people know that we'll show that number alongside the trend they're used to it and tell them to take it with a grain of salt. And if it's not something we're charging for, it's being introduced into our service, and when we feel like it's reliable and provable, that our stance might change in terms of how accessible it is, because we might be able to do a lot more with the data once we're comfortable with it. But we're not willing to show a lot of the things that we're seeing behind the scenes until we can basically explain how they work. Yes?
I have a different question.
Sure, absolutely.
If you have a model that has, say, 100 features,
Yes?
how do you know which features don't contribute? Is there a mathematical way that you can say, this feature is not contributing,
Yes.
I'm going to eliminate it from the model?
There can be. So an example is, let's say you know a school schedule nearby, and you're trying to predict traffic at a business, and then you can there is a mathematical approach, and they have some models that make it pretty easy to apply it to where you don't have to be a math guru to use it. But the gist of it is, you can basically look at that pattern and have it analyze that pattern compared to your data, and tell you, it can correlate between the two and tell you if there's any relation. And you end up with a nice, pretty grid type pattern that lets you know, yeah, this school is far enough away that it's not really influencing our traffic. That's a great question, though. There are absolutely ways to do that.
Jump in there.
Sure.
It would depend on the classifier you're using. Because if you use a neural network, very few of them will tell you what feature it's using.
Yeah, that's what I thought.
But if you're using
Well,
something like that,
this is analysis outside of. This is analysis after the fact. I'm talking more along the lines of, here's my source data, and then here's the feature that I think I should feed into my model. But before I'm building my model, I'm comparing my source data to that feature set or or that information, and I'm correlating the two ahead of time. To answer if you're talking about in real time or after you've built the model, that's a good question. I don't know that.
Well,
A
yeah.
lot of the tree classifiers will give you reports saying what features were used for the classification.
Okay. Well, I know we're way over time, and I apologize. I'm glad to stick around for more questions. So if you have more questions, feel free to stick around. And this is something that I'm super excited about. If you couldn't tell, I apologize. But I'm glad to chat. There's a lot for me to even learn. So if there are folks here who have done a lot of work with machine learning and building models, I'm sure I can learn tons from you and would appreciate hearing from you, or at least getting to know you. Were you able to